Okay, so so now the background of the neural networks. Okay, so the neural networks was introduced long time ago, in the 40 or in the 50, and they try to model how a brain works, how an actual brain works. And nowadays, neural networks are used in many areas. So used in classification problems, in image recognition, speech recognitions, and in the last 5 years, they start looking on the application of neural networks, how to solve PDEs. And I had colleagues, like worry that, okay, so in the future, neural networks solving PDE, so we don't have anything to do, So I started to look into the reality, whether neural networks can do everything. Okay, so now there are a few types of neural networks: feed-forward neural networks, okay, or multi-layer perceptrons, which is the one that I'm focused on today. And there's other type of neural networks as well, which is the convolutional neural network. So this neural networks is very popular in image processing. They try to use CNNs, on the sequence of images in order to detect the features before they feed the features into another neural networks. So this is the topic for another seminar, And then they have another type, which they call a recurrent neural networks. So essentially, in the recurrent neural networks, you can somehow feedback the signals in the last layers to the previous layers. That's why they call it recurrent neural networks. And one of the prominent type is the LS TM long short-term memory networks, and it's very popular in speech recognition. But again, I'm not going to talk about this recurrent neural network. So, so now go back to the 50. So neural networks ideas was started by perceptron, which was invented by Rosenblatt in 1958. And this is the actual electronic device, like you can see that there is an array of photocells here, right? 400 photocells, and they have some variable resistors, so you can adjust the values of the resistors. And then the input will come in from the left here. And then, the resistor will moderate the electricity currents, and then it gives some outputs. So it's a real electronic device, okay? But because we are not focusing on electronic stuff, and we just look at the perceptron from the view of mathematics, and essentially it can be represented by a simple diagram like this, okay? So you have, say, for example, you have 9 inputs. So 9 inputs like x1 up to x9. You can represent it by vectors, in R9. And then there are weights. So the weights, like in the previous pictures, the weights can be represented by the value of the resistors, And then depends on the input and the weights, then there the step function, it can be like a switch between 0 or 1, okay? And we can simplify the mathematics by introduce the dot product. So you define Z is the dot product of the vector weights dot with the vector inputs, and then B is the bias. So the bias is the one somehow is a number that depends on the configuration of the networks. And then if Z is the dot product of the weight and the input plus the bias, then the value of the output could be either 0 or 1, depends on Z is positive or negative. Okay, so this is a seamless perceptron you can have. And later on, you know, like when fuzzy logic came along, they say that, okay, the output could be a number, a real number between 0 and 1. Okay, it doesn't have to be a binary output like this. And then they just replace the function. Okay, the function, instead of a step function, they're replaced by the sigmoid function. And you can see the sigmoid function, if you take z go to minus infinity, then this one is just 0, right? And if you take z go to plus infinity, then it just become 1, right? But then in the between, it's just continuous. And that they call it a sigmoid function. And then they have other, well, the function, they call it activation functions. So they have other activation as well. And nowadays, the most popular activation function seem to be a ReLU function. ReLU is stand for rectify linear unit function. And it's very simple. And you know, you can represent it by max of z and 0. So if z is negative, then this is just equal 0, and if positive, then it's just a linear function. Okay, and it could be generalized by, you know, like you, instead of 0, now you have alpha and z. Okay, and alpha is some number less than 1, and they call it a leaky ReLU function. So there's other type of activation function as well, but those are the most popular one. Okay. And then now the structure of a neural networks look like this. So they have 3 layers. So the input layers, yeah, the input layers contain all the inputs here, and then there's the output layers. Output layers could have 1 or many outputs, and then there's a hidden layer. So this one is a simple, the seamless network. You can have the hidden layers, you just have 1 layers of neurons, but you can have 2 hidden layers like this. And when they say a D network, it means that they have more than 2 layers, more than 2 hidden layers. And I saw some papers that they mentioned networks that could have 1,000 layers. Okay, and you can see that the connection could be complicated. So this one is like X1 can fit into all the networks, I mean all the neurons in the second layers, and X2 can fit in all the neurons in the second layers, as and so on. You see the connection could be complicated like this. And then now, so how do we implement these networks, or how do we make it more precise? So we can formulate a neural networks like a sequence of matrix vectors tuples. Okay, so W1 is a matrix, yeah, of the size NL times NL minus 1. So you will see it in the next pictures. And B1 is the, I mean, B is the bias vector. So for each neurons, you have a 1 bias. Okay, and then you can have L layers. So you have first layer, second layer, up to the L layers. Yeah. So each layer you have a weight matrix and a vector of biases. Yes, a vectors of bias. So the bias for each neuron in that layer. And now, so how do you compute the output of a network? So initially, you know, the activation at 0 is just the input vector. So x1 up to xn here, well, and 0 is n, yeah. And then for the hidden layers, first you take the activation, right? You take the weights matrix, you multiply with the activation, then you plus the bias vectors of that layers. And then after you got the vector z, then you apply the activation function on the vector z. So because sigma, remember, is a function of 1 variables. So when we apply sigma to a vector zl, it just means that we apply point wise. You know, you take every element wise. Yeah, we take every element. So we take like zlj, you apply sigma zl J, and then it's become ALJ. So that's what it's meant here. Okay. So now you see in the in this diagram, we have a very concrete example. So suppose you have layer 1, I mean the input layers n0 equal 2. So you have two inputs, yeah. And then n1 equal 3. So you have 3 neurons here. Okay, and n2 is 4. And you have 4 neurons here, and n3 equal 2. So you have two neurons here. And you see for the weights, you see the weights here because you have 1 to 4. Okay, so you have W for 1, so and subscript 2 for the second layers, and here W2 3 1 because the layer is 2, and 3 1 because it's from neuron number 3. I mean from neuron number 1 go to number 3 and so on, right? And the bias, so the bias here, suppose neuron number 3, then you got B3 and subscript 2 because it's a layer 2 and so on. And now, so how do you train a network? So remember that you have a collection of n inputs. Okay, so the input are the data points. So x1 is a vector in Rn, right, or Rn0, n equal n0, and x2 is in Rn, and so on up to xn. So n could be very large. Okay, it depends on how many data points you have in the training set. But the thing we have to know is the value y1, y2 up to yn. So the y1 up to yn are knowns. Okay, and it could be a single number, right? So in that case, you just have like a either 0 or 1, or plus 1 or minus 1, true or false. It's a classification problems. Okay, but it could be a vectors, because it have, suppose you have a multi-class classification problem, so it could have class 1 or class 2. Okay, so essentially just a vectors in n subscript L. Yeah, so they are known. And now you define the loss function of the networks to be the difference between, well, I mean, you take the norm, right, of the difference, the L2 norm, the difference between the correct output yi and the output computed by the neural networks given the input xi with the activation sigma. Okay, and so this one you sum, I mean, you take the norm, you square it, you sum over all of them, and you take the average 1 over 2n. So we got it a loss function. And you see, I mean, ideally, then you want this one to be 0, right? Because that is how you try to fit the data to the correct outputs. Yeah. And but in practice, it's not easy to make it 0, but then you try to minimize it, right? And this one we call it a loss function. So training a network is you try to find the weights, so on the weights, on the vector, so on the matrices WL and on the biases BL on each level to minimize the loss function. And then, so one of the popular algorithm to do that is the gradient descent algorithm. And Steve have mentioned this one yesterday already, and it was discovered in the 50s. Well, and essentially what it does is you can represent the change in the function f, right? So here you have to assume f is a convex function and assume that is smooth. I mean, the gradient is I mean, differentiable, so the gradient is well defined. Then by Taylor theorems, for multivariate function, multivariate variables, you can write down delta F as a gradient dot product with the change in the variables plus some errors terms of order delta V square. Okay. And then if you choose delta V to be in the direction of the gradient and the function assumes it's convex, then every step you move along this direction, then you make the function smaller. Okay, so eta in the neural networks package, they call it a learning rate. Okay, and like for gradient descent algorithm, they fix the learning rate, but for some adaptive algorithm like ADA delta, very recent algorithm, then the eta can be changed adaptively for every iteration. Okay, and so the gradient descent algorithm can be given like this. So initially you put in V0 to be some random guess, and then every time you update the vector V by going down in the direction of the gradient. And the stochastic gradient descent is when the data set x1 up to xn is very large, right? Then they have to compute approximately by taking only a small collection of m points. So m is much smaller than capital N. So suppose n is 1,000,000, then m is like 100. Okay, and they choose it randomly, and they compute the loss function. The gradient, the loss function approximately like this, and they call it stochastic gradient descent. And because it's a stochastic algorithm, so every time you run the networks, the neural networks training, you might get a different results. Okay, and every proof you see in this kind of algorithms, they have to take expectation of a random set of points. Otherwise, you cannot show it is correct every time. So now one of the features that you need in the algorithm is the gradient. How do you compute the gradient effectively? And you can see that, for neural networks with many layers, computing this gradient is very complicated. But the backpropagation algorithm is somehow a very effective way to compute the gradient of the loss function. Okay, and it can be summarized in 4 equations, BP1 up to BP4. So BP1, so what it means is essentially the idea is just try to compute the gradient by backpropagate the errors at the last levels to the initial levels. Okay, so maybe make it more precise. So suppose you have delta L is the errors at the output layers, the last layers. Yeah, then the delta L could be computed by this formula. So this is the gradient of the loss function with respect to the activation, okay, in the last layers. And then so this circle dot is a Hadamard product, which means that if you take 2 vectors, okay, you just take element wise, you take the multiplication element wise, and you leave it like a vector like this. Okay, and then you circle dot with a derivative of the activation function of the ZL in the very last layers. Okay, so remember ZL is just the weights at the level L multiplied with the activation of the previous level plus the bias as the last level. And in order to show this, it just essentially just a chain rules. So if I go here, then you can see that by the chain rule, you apply the chain rules on the loss function. And remember, AK, AJ, will be equal 0 if K different from J. Because, remember, the activation is computed pointwise, yeah, by taking the component of the ZL. Okay, so then the consequence of the chain rules will make this sum simplify into only a single term like this. And then, you know, I mean, you rearrange it and then you write down, then this one is PP1. Okay, so there is other three equations. It can be proved by the chain rules. Yeah, but essentially when you got those four equations, then you can compute the gradient of the loss function easily. Okay, so that is the backpropagation algorithm in the next slide. So first, the first step is they set the activation in the input layer, and they feed the activation to the networks to the very last layer. Okay, so this one is from the definition how you compute the value of the output of the neural networks. Yeah, and then once you have it, then you got the output errors. Okay, using this BP1. Okay, and then after that you backpropagate the errors using the second equation BP2. Okay, and then after that BP3 and BP4 give you the loss function, which is, sorry, the gradient of the loss function, which is just partial derivative of the loss function with respect to the bias and with respect to the weight. And then this one can be used in your stochastic gradient descent algorithm. You know, so this backpropagation makes the training of the neural networks very fast. Yeah. And now, so SIAM optimization. So the one of the famous variants of the stochastic gradient descent is SIAM optimization, and this paper was published in 2015. So you know, recently, very recently, right? So it's around 7 years ago. But now, like Steve said last night, it attracted more than 115,000 citations already. Okay, and it's very popular because, you know, I mean, based on my experiments with my students, it performed better than other algorithms, and so far I don't know why. And in this paper, you know, I mean, they prove that it can converges with the rate 1/√n. But I think Steve, he doesn't believe it. It's correct proof. But anyway, so essentially there is some new ideas here. So before you apply the stochastic gradient descent step, right? Then they have some what they call a moment estimates. Yeah. So you can see that the moment estimates somehow makes the algorithm works better than just a simple learning rate eta at the step when you update the gradient. So now there is some parameters, the step size alpha, the beta1 and beta2. So the beta1 and beta2 actually are very close to 1. Okay, they say that you should use 0.9 or 0.99. And then the algorithm is like this. So you can see that in every step, you compute the gradient. Yeah. But then they introduce the first moment estimates and the second moment estimates. So this one, the GT is the gradient of the stochastic objective function. Okay. And you update the first moment estimate by this formula. Yeah. So this one is the moment in the previous step, and this one is a gradient, is a current step, and it's just a linear combination of the two with a beta1. So beta1 is between 0 and 1, but practically it's very close to 1. Okay. And then the second moment estimate is previous second moment estimate plus GT squared. So this one is a vector, And you take every element and you square each element. Then after that, they also correct the first and the second moments by what they call a bias correction. Okay, and with this, then they will update the new xt, so the alpha is still a fixed rate, but I mean the gradient now has this form, yeah, with some moment estimates. And this is the Adam algorithm. And then I look around and I found that there's some other papers that show that in theory neural networks with at least one layer can approximate any continuous function to any arbitrary accuracy, like you can make it the errors less than epsilon, but again this one is just a theoretical results. Okay, and they don't show you how to construct the approximation. And then there's other papers with approximation rates for function with extra smoothness, okay, for sigmoid function or more general activation function. So those papers by Pincus and Maska. So Maska, actually, I look at his paper and actually he just proved the results for neural networks with only one layer. Okay, and the activation just a Gaussian. Okay, so now we go to the application. So the first application is credit risk classification. So Michelle, she used neural networks to try to classify risky customer. So risky customer is defined to be like some people who borrow the money from the credit card company and they fail to repay their loan within a deadline, and so they have some kind of data like this. And there we have found a data set from Cargo. So it's like it's a real data set, but they have made it anonymous, so they anonymize on the customer. So what you have is just a collection of 8,000 entries of about 1,000 customers, and then they have a features for each customer. They have some features that again they do not give the description of the features. Yeah, so just anonymized features. And then there is features that we have to notice that the data is imbalanced. So what does it mean? It means like in 1,000 customers, there's very few customers that risky. There are always good customers, because if you don't pay, your credit card companies knows how to go after you. So that's why the number of risky customers are very low. So the data is imbalanced. So somehow we cannot use the data directly to fit into the neural networks. So we have to do some what they call an oversampling. So oversampling can be explained by these pictures. So suppose you have an original data set like this. So you have a majority set, like non-risky, and the minority set is a risky customer. And you can make it balance, yeah, by choosing some random customers here, and then you duplicate it. And we duplicate it so that the ratio between the two classes are the same. Okay, so we call it oversampling. Or you can duplicate up to a certain point that the majority over the minority is equal R. R is some number between 0 and 1. Yeah. And so there's undersampling as well, but we don't use this because the minority class is very small. So undersampling will make the data set smaller. Then the data set also contains some extra information. Yeah. So the customer data set is the standard data set already with 24 attributes, but the payment data is that they have some extra information like what is the total number of times overdue and what is the total overdue sum, something like that. Yeah. And then we just use that payment data, and then we introduce 2 new features into the original data set. And then we try to experiment with all the possible parameters. Yeah. So you can use random oversampling on the whole data set or on the training set. And then you can change the number of layers of the networks. You can change the number of neurons per layer. You can change the sampling strategy. You can train the so you can change the training and testing ratio, and then you can change the activation function, ReLU or sigmoid function, and then you can change the algorithm as well. You know, you can choose either ADAM algorithm or ADA delta. So ADA delta, I didn't mention about this, but essentially, you know, like in the learning rates, you can make the learning rate adaptive according to the loss function at every step, or the stochastic gradient descent. You know, so this one is popular, and we can use or we can omit the payment data to see whether it improved the classification rates. And then the confusion matrix, you know, so confusion matrix, you have a 2x2 matrix, you know, like the number of true negative, false positive, false negative, true positive. And based on that, you can define what is the precision on the non-risky, where it's just a true negative, yeah, true negative here, divided by true negative and false negative. So you take essentially the ratio between these entries and you divide the sum of the first columns. And precision on 1 is the same for the second columns. And then the accuracy is like you take the true negative plus the true positive, and you divide it by the sum of all the entries of the matrix. And then a table of results looks like this. You know, you see that for a different test size, you know, your accuracy can change. This one is like 90% training set and 10% is for testing. And then you see the accuracy is 0.84, so 84% accurate. And then we try many combinations. So there is totally 26 combinations, and we try to draw the conclusions. So essentially, the conclusion is, you know, oversampling have to be done over the whole data set before you apply the learning. And then, you know, you use ReLU, give you a better results, and ADAM is the best optimizer. Okay. And then, okay, so the next application also about the classification problem. So for detecting Alzheimer's disease. So Alzheimer's disease is a type of brain disease, yeah. And the thing that we have to pay attention is the reduction of the cortical thickness of the brain. And now I can show you the pictures. What does it mean here? So the cerebral cortex is the thin membrane around the brain. Yeah. So maybe look at these pictures. Yeah. So essentially, you know, when you cut the brain in the cross section, then inside this one is the white matter, and the top layer is the gray matter, and the thickness of this one is, we call it the cortical thickness. Yeah. And essentially in the Alzheimer disease, then you see that the cortical thickness is decreased. Okay. So this is important because, you know, when we got the data, so the data is just MRI scans, yeah, and each of them is just a discretized surface with around 260,000 vertices, yeah, and then they have triangular faces that connect the surfaces, and then we plot it using MATLAB. We can plot it like this, yeah. So this one is an example of a surface. So this one is AD. It means that you know, like a brain scan that has Alzheimer's disease, and this one is just a number of the patient. And then, I mean, if you put this full brain scan into the neural networks, then it's very slow and it's very impractical, right? Because, you know, I mean, you can see the naive approach is to take a neural networks with 260,000 inputs, yeah, and then who knows how many layers in the between, and then it will be very slow. Full data set is around, you know, 76 million entries already, and then we try to reduce the data, you know, to some simple feature matrix, and then we fit into the neural networks. So then we found a paper, you know, in a medical journal, yeah. Somehow it say that, you know, you don't have to look everywhere in the brain, but you just look at the cortical thickness as 9 particular regions, okay? And those 9 particular regions on the brain, they have a name here, and we don't understand exactly what it means, you know, but it has a name. So suppose ITG, you know, inferior temporal gyrus. And then if you look at those thickness at those 9 regions, then you can find out, you know, whether the patient has Alzheimer's disease or not, okay? And that's what we did. So suppose that, you know, you take a brain scan, then you can plot the PHG region like this. So this is the red dot here, very tiny dots, and you have 9 regions like this, yeah. And so this one for the AD for the Alzheimer's disease patient, and this one control patient, this means that the normal patient, and you see that is different here. And so now if we just extract the thickness over those 9 regions, okay, then it's just a very small matrix with about 2,600 entries, okay. And then those matrices become the features matrix, and you use it for the input of the neural networks. So this is the plot of the features matrix of the control patient over 9 regions. So you see 9 regions here, yeah. And so this is the on the y-axis is the patients. So for each patient you have a different values, yeah, but it in the same, well, not in the same, but in the you know, very similar category, yeah. And then so this one region 1, region 2 up to region 9, and this one control patient, this means that they don't have disease, they don't have Alzheimer. And this one is the one that who has Alzheimer disease, yeah. And you see that, you know, the 3rd and the 7th columns significantly smaller than, well, not significant, but you can see that the values are smaller, okay, for the Alzheimer's disease. And then we use the collection classification rate to check our algorithm. So now, you know, you can see that we use a different training size, 40% of the full set, or 50%, or 60%, or 70%, okay. And then you see that with 70% of the full set to be the training data set, then we we have up to 90% accuracy rate. Okay, so this one is on the ADNI data set. And then we also use another data set, Myriad. So the ADNI data set provided by Uni of Southern California, and the Myriad provided by Imperial College London. And then you see that it also performed very well, you know. So with 70% with the training set, the neural networks can give you up to 98% correction rates. Okay. Okay, and the confusion matrix look like this. You can see that, you know, the confusion matrix like before, so it looked very good. Okay, and the last one I want to mention is about neural networks for solving PDE. Okay, so this one is relatively more recent. I mean, I saw papers like around 2017, 2018 by a group of collaborators with Canadian Dakis, and they solve the PDE by what they call a physics informed neural networks. So essentially, you know, I mean, they assume that you know the exact solution at a certain point on the domain, and then you design the loss function around that. And then neural networks can be solved, can be used for high-dimensional PDEs. You know, so this is a famous paper by Han, Jensen, and Vinen, 2018. And then deep neural networks for high-dimensional PDEs. So there's more recent papers here and other papers. So, but essentially, I want to try to do some simple PDE. Okay, so Callum Scott helped me with this. And so we use PyTorch and an extra package built on top of PyTorch. And then you see that backpropagation is used to calculate the derivatives. And then you see, once you have a neural network solution, then you can compute it. You can derive the solution anywhere on the whole domain. So now let me introduce the seamless one-dimensional advection equations. So you have a equation U. You have an unknown solution U, which is a function of time and space. Okay, so time we assume that from 0 to 1, and x is just from 0 to 1. And then we have a mesh for x, for time, and for omega. And then we have initial conditions, you know, assume that when time equals 0, it's just a sine function. And then we assume the boundary condition, you know, like when x equals 0, x equals 1, they're just the same for every time. So now, so remember in the neural networks, the key features is a loss function. So in this case, you define the loss function is to be the PDE, right? Evaluate at some random points in the interior, right? And remember, you want to minimize it. Actually, you want to be equal 0. So the loss function L1, you know, it's just the square of this, you know, the left-hand side of the PDE over the evaluation points, interior. And then the second loss function is the one on the boundary, right? Oh, no, initially when time equals 0. And the third loss function is for the boundary condition between, you know, like at the point x equals 0 and x equals 1, you know, at every time t, it has to be the same. And we try to minimize the mean square errors of L1, L2, and L3. And so the results like this, you can see the neural networks is the, well, in this case, we know the exact solution. So the exact solution is the red curve, yeah? And then the neural networks is the blue curve, okay? So it is very, very close to the exact solution. And the green curve is the upwind finite difference scheme. Okay, so there is a finite volume methods for solving this type of equation, and you can use upwind difference scheme or central difference scheme, and it has either the yellow or the green one. So it's a bit further away from the neural networks. Okay. And then we try it for another equation, which is the elliptic equation on the sphere. And the equation look like this. So minus delta, the delta S here, just the Laplace Beltrami operators of the sphere. And the function is, F assumed to be in some Sobolev space. And, we have existence and uniqueness. We can solve it by spectral method. We can prove it. The convergence is L to the minus alpha if the function belongs to Sobolev space H alpha. But the spectral method, we have to have a quadrature rules. Yeah. What is a numerical integration rules that integrates spherical harmonics up to a certain degree. But now we try to use neural networks, to avoid the quadrature rules. Okay. And that is exactly what we do. And first we have to discretize the equation. We have to discretize the domain. So on the sphere, we use Fibonacci points, okay, which is defined by this formula. And we use spherical design computed by Rob Mosley, who is in the audience now. And the figures of the points on the sphere look like this. So, it's somehow well distributed on the sphere. So these are the Fibonacci points. And this one is spherical design points. Yeah. And now the loss function is just the PDE, right? You evaluate on the discrete set of points. So xi on the sphere. Okay. And so in this case, we assume that u is some given known functions. Yeah. And then we use it to fit in the loss function. And we have, we try different activation function, but it seems that the log sigmoid give the best results. And again, the Adam algorithm somehow give the best results. So, and we use different layers, different number of layers, different number of units. But in the next figures, I just show one case with 4 layers, 32 hidden neurons per hidden unit. And then the batch is like when you use the stochastic gradient descent, you choose a small set of points. Yeah. And you can see that, so this one, the L2 errors is plot here. So with Fibonacci points from 10,000 to 60,000 points, and somehow it decreased like 1/n. Yeah, decreased like 1/n. Okay. And so for efficient spherical design points, then the numerical errors here, the blue one, and this is the curve 1/n. And we also increase so this one is up to 40,000 points. Yeah. So we also increase the number of n to 500,000 points. Yeah. And somehow the rate is still 1/n. Yeah. But we cannot prove it yet why it's 1/n. So it's still a mystery, but it seems that the rate of conversion is 1/n. Okay. Well, so in conclusion, I've tried neural networks for classification problems. Yeah. And then we apply the techniques for imbalanced data set, for MRI image recognition, and for solving 2 PDEs problems. But, it seems that for practical application, you have to pre-process the data before you can fit in the neural networks. You cannot use neural networks directly with the raw data. And then, there is many approximation theories of the neural networks are still unknown. So there is still a lot to be discovered, especially for deep networks. So then I think that is the end of my talk. And thank you for your attention.
Thanks a lot, Thong. We have a few minutes for any questions if people would like to field some questions. Nadia?
Yeah, I have actually two questions.
Yes.
So the first question, just to make sure that I understood correctly. So when you are talking about partial differential equations, so basically